Hi, everyone. I thought I would record myself doing some integrals, specifically the ones that were suggested by the professor for midterm practice. I haven't looked at these yet. I mean, I've written them down from the textbook, but I haven't thought about how to solve them. So you'll be seeing my problem-solving process in real time. That might mean there could be some hiccups. I don't really know. We'll see. Some of these are kind of tricky, so we'll see how it goes, but hopefully seeing my thought process helps. And yeah, this will take as long as it needs. I'll add little timestamps into the YouTube video, so you can sort of click along to whichever problem you want. But yeah, for now, let's dive right into it. So we're not going to do anything from 7.1 because I think I already covered all those problems, all the recommended problems in section. So feel free to look through my section notes for those. So we'll dive into trigonometric integrals. This first one, I immediately see cosine squared, and I think, oh, since I have an even power of cosine, I'm probably going to have to use that half angle formula. That tells me that cosine squared can be written as 1/2, and then this is 1 plus cosine 2 theta. Okay, and then I think to myself, well, I could integrate it as is, or I could split it up into 2 separate pieces and integrate separately. Let's do that just to make it look nicer. So this first integral, if I distribute the 1/2 through, just becomes the integral of 1/2 d theta. Second integral is, I guess I could pull the 1/2 out if I want to. Again, I'm doing this off the cuff, so might be a little messy from time to time, but here we go. This first thing should integrate to 1/2 theta. Then I'll plug in my bounds. And the second one, okay, I'll have a 1/2. And then let's just prepare ourselves. Now I'm thinking to myself, okay, I could perhaps have memorized the antiderivative of cosine something times theta, or I could do a u substitution. So say u equals 2 theta, go through that process. The way I like to think of it is just, okay, if I were taking a derivative, it would be, the 2 would come out, and then I'd say derivative of cosine is negative sine, and then leave the 2 theta. Antiderivative, I do the opposite. So instead of a 2 coming out, a 1/2 will come out, because antiderivatives are the opposite. They're supposed to sort of cancel out. And then antiderivative of cosine is sine, and then leave the 2 theta. So that's how my brain does it. Then if we plug in here, I get, okay, 1/2 of theta. So theta could be pi over 2. That makes it 1/2 of pi over 2, which is pi over 4. The 0 doesn't do anything, so no worries. And then over here, if I plug pi over 2 in for theta, well, 2 times pi over 2 is pi. Sine of pi should be 0. So that's great. And then similarly, sine of 0 is 0. So looks like that should be pi over 4. And you know what? Maybe since I haven't prepared these, anytime I finish a problem, maybe I'll look in the back of the book. So yeah. All right, so I paused the recording and checked. Pi over 4 is correct. Let's move on to the second one. Again, I see even powers of sine and cosine. I'm thinking, okay, I probably have to do the exact same thing. By the way, I'm going quick just because you have the ability to pause since we're recording this. So sine, let's just immediately do this. Let's say both of these are going to have a 1/2 blah in front of them. So let's take both of those 1/2s and just pull it out front. So 1/2 times 1/2 is a 4th. So I'm not going to worry about that part of the half angle formula. And then for sine, it's sort of the opposite of what it was for cosine. So it's 1 minus cosine 2 theta. And then for cosine squared, get the 1 plus cosine 2 theta. Remember, I pulled the 1/2s out already, so we don't have to worry about those. And then I probably FOIL this thing, which is nice. It's almost like multiplying by the conjugate. So I get the outer terms, I get the sorry, what am I saying? I get the first terms, I get the last terms. So that's 1 minus cosine squared 2 theta. And then the inner and outer terms should cancel. Plus cosine 2 theta minus cosine 2 theta. So that's nice. And then looking at that, I guess there are a couple of things you might think. You might think 1 minus cosine squared is sine squared. Yeah, that's probably a nice thing to do. So let's do that. 1 minus cosine squared is sine squared. So this becomes sine squared. The argument was 2 theta. So I'll keep that. And then, okay, I'm back to the previous problem again. I have an even power on a sine function. I probably want to use the half angle formula again, which is one you should have memorized. So this becomes 1 minus cosine, and I get a 1/2 again, right? So let's make this 1/8 out front. So pull the 1/2 out. 1/2 times 1/4 is 1/8. And then this would be 4 theta now, because whenever you use the half angle formula, it sort of doubles. I don't know why I switched from x to theta, but same difference, right? It doesn't matter what your variable is. Apologize if you were confused about that. It's using theta up above, so I guess that's where that came from. Anyway, cool. So we get 1 minus cosine of 4 theta. And then let's just do this one really quickly now. I could split it up if I wanted to, but I know the integral of 1 is just theta. I know the integral of cosine 4 theta, well, negative cosine 4 theta should be negative 1/4 sine 4 theta. Plug in pi over 2 and 0, see what we get. Again, these should be nice to plug in. So when I plug in pi over 2, 4 times that is 2 pi. And sine of 2 pi is 0, sine of 0 is 0. So this term won't ever matter when we plug in our bounds. So it should just be 1/8 and then pi over 2. So that is pi over 16. Again, I'll pause the video and check my work. Looks correct. So let's move on to the next one. This is one of the ones where you have to, it actually tells you the answer, and it asks you to prove that the answer is true, but let's just figure this out on our own. There's something called a product to sum formula for this guy. It's like a special trig identity for if you have two sines or cosines multiplied together. This is one you wouldn't be expected to know, so it would be given to you if you were supposed to use it. In fact, I don't have it memorized, so I'm just going to check my formulas down here. This is 1/2, and then in parentheses, I'll get cosine of the first argument minus the second argument. So mx minus nx. And then I have a minus cosine, and then I add the two arguments. So mx plus nx. You guys have probably seen your homework problem that looks like this. Instead of mx and nx, it's like x and x plus 1. So you can use this strategy for that homework problem too. Let's see. So I'll pull this 1/2 out so we don't have to worry about it. And this is interesting. At this point, I'm thinking to myself that some nice things might happen because of these symmetric bounds. Because cosine is an even function. Yeah, so that should work nicely. Anyway, that'll come into play later. Let's just write what this should look like normally. So cosine, I could kind of factor the x out of these. So that would look like m minus n times x. Let's split this up into two integrals while we're at it. So the 1/2 coefficient goes on both of them. And then this would be a cosine m plus n times x when I pull that x out. Cool. And then you can integrate these like you usually would. Do I want to? Yeah, let's forget about what I said about the symmetric idea. I mean, you could do it if you wanted to, and I think it would be fine, but whatever, it doesn't matter. Second thought, it would make my life easier. All right, so let's do this. Let's remember the fact that if I'm going from negative a to a, and I have an even function, then graphically what's happening is this. Even means your function, no matter how weird it looks, is symmetric about the y-axis. So the area to the left from negative a to 0 is the same as the area on the right from 0 to a. So you might as well just calculate one of those things and then double it. So let's do that. So I would get the 1/2 goes away because I'm doubling this integral. I'm going from 0 to pi. Sorry, what am I saying? That's wrong. Yeah, no, that's right. Okay, cool. Yeah. Writing this. Is like saying, okay, I'm doing the right half of some integral, which should be exactly half of the full integral. So there you go. That is sound. And then you can do the same thing over here, because I mean, in each case, cosine's an even function. This goes from 0 to pi, cosine m plus n times x. You don't have to do it this way, of course. That's just a fancy step in the middle to save ourselves some algebra work down the road, because it's nicer to plug in 0 than it is to plug in negative pi most of the time. Anyway, integrating this, you're just going to treat m minus n and m plus n like constants. So it's the same story that it has been for the other ones. Your integral of cosine is sine, and then you're just going to divide by this coefficient. So 1 over m minus n sine m minus nx. And you go from 0 to pi. And at this point, I have to issue a warning, which is whenever you divide by something, you better make sure it's not 0 you're dividing by. Okay, so we're actually going to split into two cases here, one where that is 0 and one where it's not. So maybe I'll write it like this. Bump it over, and we'll do a sort of piecewise thing. So, and let's keep going with this. So the second integral would look like 1 over m plus n sine, let's wrap this, m plus n times x. Okay, and I have to plug in my bounds of 0 and pi. And we'll say, so this is true if m minus n is not 0. And similarly, m plus n shouldn't be 0. But I think in the problem statement, they don't allow that to happen. So we'll forget about that. Okay, the second thing that could happen is like, okay, what if these are 0, right? What if m minus n is 0? Then what are we going to do? Well, if m minus n is 0, then m minus n times x is 0. And if m minus n times x is 0, I'm just looking at cosine of 0, right? So since I'm just looking at cosine of 0 is 1. So really that whole integrand simplifies to just 1, which is pretty nice, I suppose. Yeah, and I just went back and checked, and m is assumed, m and n are both positive integers. So you're never going to have the case where m plus n is 0. Anyways, that's a side remark. So what we need to write here, because I don't need it quite as big as it was, is that if this is 0, then cosine of 0 is 1, and I'm just looking at the integral of 1, right? So integral from 0 to pi of 1 dx, but 1 integrates to x, So I mean, I just have this thing for the first integral. And then the second integral, well, I mean, we said, this is never going to be 0. So the second integral is going to be the same. Let's just copy paste it maybe. This thing. So this is if m minus n is equal to 0, it's a sort of special case that you have to consider. Okay, and then we figure this out. And we say, okay, well, if I were to plug in, if I plug in pi for x, well, the nice thing about sine is any integer multiple of pi plugged into the sine function gives you 0, right? And m minus n is going to be some integer, right? Because both m and n are integers. So that term is 0. Also, if I plug in 0, I get 0. So that term goes away. And then similarly over here, right, again, you would get an integer multiple of pi, or you would get 0. And so on top, you get 0. And by the way, I'll rewrite this condition. M minus n not equal to 0 means m is not equal to n. 0 if m is not equal to n. And then on the bottom, okay, well, same story. This second piece is going to be 0 again, but this first piece is going to be pi when I plug in my bounds. So pi. And similarly, m minus n equals 0, just move the n over. That means m equals n. And I believe, again, I'll check the book. I believe that's what we were looking for in 76. Yes, 0 if they're not equal, pi if they are equal. Okay. So that's how you prove that. The only tricky part is the fact that you have to break into cases depending on whether or not you're allowed to divide by m minus n. So there you go. Let's move on to 7.3, which should be trig substitution. Okay, so number 1 looks like this. I think this was one of the problems that said set up the integral but don't evaluate it, but we might as well evaluate it if we can. So I'll do my best. What I'm thinking here is I know a nice trig identity. That looks sort of like this, 1 plus something squared. In fact, 1 plus tangent squared is secant squared. So if I could make the substitution x equals tangent theta, then we'd be good to go. We would get probably just a secant on the bottom. It's also useful to figure out dx, so derivative of tangent is secant squared. So we have that. So let's go ahead and plug some stuff in. So on top, x cubed, well, if I'm replacing x by tangent, that becomes just tangent cubed. On the bottom, I get 1 plus tangent squared, but we already said that's secant squared. And then dx is exactly secant squared as well. So I get secant squared out here. Okay, of course, square root of secant squared is just secant. I have a secant squared on top, so one of those will go away because there's a secant in the denominator. And I'll be left with a tangent cubed times secant theta. D theta. Then I have to dust off my tangent secant trig integration techniques. You could also convert these to sines and cosines. I believe that's always a valid technique. So if you only want to remember one thing, feel free to convert them to sines and cosines and go from there. But just for practice, let's see what I can do here. I see an odd power of tangent. I think to myself, it would be good to save one of those tangents and get rid of the rest of them. By get rid of, I mean, okay, save this one, turn a single tangent squared into secant squared minus 1. Again, that's from this identity. Just solve for tan squared. And then I have a secant hanging out on the end still. And then we look for some nice substitution. I'll just note over here that if I choose u equal to secant theta, then, okay, the only way this is going to be a good substitution is if du also appears, and the derivative of secant is secant tangent. Let's move this a bit. Okay, so do those both appear? Yeah, this will be like a u squared minus 1. And then looky here, that's a secant tangent d theta. So that's du. So great, I have u squared minus 1 du. Integrating that gives me 1/3 u cubed minus u plus a constant. Put your substitution back in. So this is secant cubed theta minus secant theta plus an arbitrary constant. And once you're done integrating, you're going to have to get back into the world of x's. So I can do that by looking at my substitution and saying, okay, if I drew a right triangle representing that substitution, I want tangent theta equal to x. That's the same as saying tangent theta should be x over 1, but tangent is opposite over adjacent. So x should be the opposite side. 1 should be the adjacent side. Pythagorean theorem says this should be the square root of the sum of the squares. And now looking at this, I could say to myself, well, secant theta, secant's 1 over cosine. Cosine's adjacent over hypotenuse, so there should be hypotenuse over adjacent, which is this square root term over 1. So just the square root of 1 plus x squared. Okay, so plugging that in, I get this. I guess looks kind of funky, but oh well. 1 plus x squared, whole thing cubed. And square root of 1 plus x squared plus c. And we don't have any numbers to plug in, so we're done. I guess you could simplify it a bit if you want, but that's fine. All right. Also, maybe worth checking this answer. So it's looky in 7.3. And oh yeah, they don't have this answer in the back of the book. So hopefully that's correct. If not, let me know. There's a problem about the volume of a torus. Maybe I'll record that separately. Let's skip over it for now. And let's go into partial fractions. So, okay, I see a partial fractions problem. First thing I think to do is split it up. For this problem, I have two linear terms in the denominator, and linear terms are nice because that tells me I can just use a constant on top of one and a constant on top of the other. Then I multiply both sides by this big denominator. You don't have to write this every time, by the way. I just do it for you guys. So then this looks like I get 5 on the left. I get a times x plus 4 plus b times x minus 1 on the right. And then there are always two ways to solve these. Let me look at some other problems and see. Yeah, we'll get to see a different way. So the way I like to solve the simple ones is choose nice values. Namely, values that'll make some cancellation happen. So for example, if x equals 1, then this becomes, so the equation becomes a equals 1, or 5 equals a times 1 plus 4 plus b times 1 minus 1. So that's good. The b term goes away. I'm left with 5 equals 5a, so a equals 1. And then we're going to do the same thing to kill the a term and solve for b. So killing the a term means setting x equal to -4. So we get something like 5 equals a times -4 plus 4. So the a term goes away. And the b term becomes this. And okay, solving that, I believe you get b is -1. Whew, great. So plugging all that in, the integrand becomes 1 over x minus 1. And then b was -1. So I'll put the minus out here, x plus 4, wrap it in parentheses, write a dx on the end, and then integrate piece by piece. So 1 over x minus 1 dx minus 1 over x plus 4 dx. And this was one I showed you guys a formula for. So we can just get it straight off the bat that you just turn these into natural logs, remembering that you have to be careful if there's a coefficient in front of the x, but this time there's not. And that should be our answer. So cool. This is one I can check. So number 7, does that look correct? Yes, it does. Cool. All right, next one. So this is sort of similar, except we have a quadratic term on bottom. So let's remind ourselves how that works. Again, partial fractions says the way we split this up depends on the terms in the denominator. So the first term is an x minus 1. That's linear, so I can put just a constant on top. The second term is a quadratic, which means I need to put a linear term on top, bx plus c. Okay. Again, I multiply by the denominator on both sides, leaving only the numerator behind. And then on the right-hand side, you get this, bx plus c times, this would have an x minus 1 on it. At this point, it's useful to actually maybe distribute, right? So whenever you have quadratic terms, it comes in handy to know a slightly different technique for handling these. So let's FOIL this stuff on the right. So I get a bx squared for the first terms. For the outer terms, it's a minus bx. Inner terms, it's plus cx. Last terms is minus c. And then you're always going to want to group these by like terms. So notice here I have ax squared plus bx squared. It's the same as a plus b quantity times x squared. Next up, we're going to look at every term with an x. Looks like it's just those two. So that is negative b plus c times x. And then the constant terms. Constant terms are 9a negative c, so plus 9a minus c. All right, then the thing to do is think to yourself, well, I have a quadratic on the right. The only thing that could possibly be equal to is a quadratic on the left. Doesn't look like a quadratic, but you could make it look like one, like so. And then you're going to set each of these coefficients, so the coefficient in front of x squared, those must match. The coefficients in front of the x terms on either side must match, and the coefficients or the constants must match. So that gives us a system of linear equations, 3 of them to be exact. So we get a plus b, the coefficient in front of x squared has to be 0. B, I guess I'll write it, doesn't really matter how, whatever, I'll keep it the same. Negative b plus c is 0. And then the constant term has to be 10. So 9a minus c better be 10. And then you solve this however you want to solve it. I like to, I don't know, let's start with the middle one. No, that's dumb. Let's start with the top one. I mean, nothing's dumb. It's all going to work out. But b has to be negative a from this. So I could take this fact and plug it in for b here. All right, so this says, actually, let's write it like this. Draw a little diagram of implications. So these two things together imply that negative a plus c is 0. That's the same as saying a plus c is 0, so c is negative a. So let's just write that to be brief. And then all of those things together, I guess just that one. So let's do this and this. Plugging in negative a for c here gives me 10a equals 10. Oops, sorry about that. 10a equals 10. So a equals 1. But if a equals 1, well, b is negative a, and c is negative a. Sorry, I should put an equal sign there. All right, so a, b, and c are 1, -1, and -1 respectively. That lets me rewrite my integrand as 1 over x minus 1. That'll be nice to integrate. And then I guess I could write it like this. If I pull the minus sign from both b and c out front, then I could write it as x plus 1 over x squared plus 9. By the way, maybe I should have mentioned this to start with. The first thing we should have done is make sure the denominator here is factored completely, but it is. There's nothing you can factor x squared plus 9 into, unless you want to talk about complex roots or something. So we're fine. This is what our equation looks like. I look at this thing and I'm thinking, how do I integrate that? I probably want to split it into 2 fractions and handle each separately. So let's do that. In fact, let's split it up into as many integrals as we can. So the first integral is this. Second integral will just be x over x squared plus 9. Third integral will also get a minus sign. And this time it'll be the second half of this fraction. So 1 over x squared plus 9. Okay, the first one is the one we have a formula for, la-di-da. The second one you stare at for a minute and you think, ooh, I have x squared on the bottom and x on top. That's prime situation for a u substitution. So pick u equals to the denominator. Du would then be 2x dx. But I don't have a 2x dx, I have an x dx, so I have to balance out with a factor of 1/2. So this is minus 1/2. And then this is just 1 over u du at this point. And then we'd have to figure out what to do with the third integral. Looking at that, I think of arctan, right? And I don't know, maybe you have a formula for this one. I think they do give you a formula in the textbook for an integral of that form. So maybe I'll just use that. Maybe I'll write it down first. So anything that looks like this, I believe you can actually solve this with a trig substitution, funnily enough, but whatever. The idea is you'll always get 1 over a arctan x over a plus constant. Okay, so we'll just use that. Here, a squared is 9. So a is 3, so I should get a 1/3 arctan x over 3. Tack a constant on, finish up this final integral, which isn't bad. 1 over u integrates to natural log of u, and we know u is x squared plus 9, so this is minus 1/2 natural log of u, where u was this guy. And keep the rest the same. That's about as simple as I'm going to be able to get it, I believe. So let's check our work in the back of the book. Number 23 this is, and that looks totally fine. All right, cool. So that's partial fractions for you. Then you get thrown into the strategy for integration section, which is just, I throw a bunch of random integrals at you and don't tell you how to solve them. Well, I will tell you how to solve them. The book doesn't. By the way, if you haven't tried these already on your own, you absolutely should. It makes no sense to watch me do problems in front of you. Math is, people say all the time, math is not a spectator sport. You actually have to like get in and do it yourself if you want to understand. So here we go. This immediately looks like a u substitution for me, right? So same story as last time. Pick this denominator for u, then du would be 2x dx. I'm missing a factor of 1/2, so I get something like this. And then I integrate that to get natural log of u. Plug back in for u is 1 plus x squared, and we're done. Not too bad. Second one, That's literally just the antiderivative of arctan. So very nice, no work required. Don't forget your plus c. Third integral. These are all meant to look similar, but require different techniques. Third integral, I'm like, oh, this stumps me for a second or two. And I think to myself, that almost looks like a trig substitution, you know, if I had a square root or something. In fact, a trig sub might work here. You could try it. Maybe I'll show you how to do it. But I might be able to get away with a better technique. And let's see what that better technique is. The better technique is, what if I made the top look like the bottom? Of course, I'm not allowed to do that. I can't just toss a minus x squared on, except I can if I balance it out. I'm adding 0, I'm not doing anything too crazy. And so, okay, let's write this out. 1 minus x squared plus x squared over 1 minus x squared. And then I think to myself, I could split this into two fractions, namely those two pieces. Right, so this becomes, whoops, 1 minus x squared over itself is just the integral of 1. And then plus x squared over 1 minus x squared. Looking at that, I don't like it that much, but could I salvage that is the question. U sub doesn't really save me here, I don't think. There's probably something smart I could do, though. Again, you could probably get away with a trig sub. So yeah, I mean, I said I would start with a trig sub, right? So I could have started by doing like x is sine theta, and we could have seen where that went, but we're going to end up doing it anyway. So let's do it on this side. So let's continue this thought process and be like, okay, well, integral of 1 is x. And then over here, I could make a substitution. I could be like, okay, what if I pick sine theta? Then dx would be cosine theta d theta. Maybe this will work out okay. I honestly have no idea. Like I said, I didn't prep these in advance, but I'd get a sine squared over 1 minus cosine squared, and then dx is cosine theta d theta. Okay, so this looks like this. On the bottom, 1 minus cosine squared. I don't know why I wrote cosine. That was supposed to be sine. Hopefully you caught that as I was doing it. Anyway, 1 minus sine squared is cosine squared. So this is really sine squared over cosine squared. And I still have 1 cosine hanging out here. So I get a little bit of cancellation. And this looks like sine squared over a single cosine. And then this should work now if I make another substitution. This time I'll do a u sub, right? And I think of u sub because I have a function and its derivative. Actually, no, that's not going to work because cosine's on the bottom. So that is slightly annoying. In that case, probably want to do, oh, I don't really want to do a half angle. D theta really messed my idea up, huh? So this might just be a bad road to go down. No, maybe. Okay, there's a way to salvage it, right? So this is uglier than it needs to be, but you could go from here and say that this is, let's just scoot this up so I have room. Like I said, I'm thinking these up on the fly, so stick with me. This won't be the most beautiful. Sine squared is 1 minus cosine squared. Okay, so I could write 1 minus cosine squared over cosine. And then I could split this up again into two fractions. I hope I'm not going backwards or anything. We'll see. So this will be 1 over cosine for the first one, but that's secant, minus cosine squared over cosine, that's just cosine. Then the question is, do you know how to integrate secant? Maybe not. I'll leave a little blank here. Actually, yeah, maybe this is one you've learned, I'm not sure, but the integral is this. And then the integral of cosine is sine. So you get to here. And then you have to go back into the world of x's, right? So you look back up here, you say, to get back to x, I need a triangle relating theta to x. I wanted x to be sine theta. Sine is opposite over hypotenuse. I want that to be x over 1. So the opposite should be x. That should be 1. Pythagorean theorem says this will be a 1 minus x squared under a square root. And I'm looking for secant, I'm looking for tangent, I'm looking for sine. Well, I have sine, so that's good. Let's write in what we do know. X plus natural log of something. Sine of theta is x. So those will actually, I don't know why I put a d theta on here, my bad. I meant to write plus c. So these x's will cancel, I guess that's nice. And then secant, let's use yellow, is 1 over cosine. Cosine's adjacent over hypotenuse, so that's hypotenuse over adjacent. It's going to be 1 over that. That tangent is going to be opposite over hypotenuse, or opposite over adjacent. I always say it wrong, which is x over that. We're adding those two things together, right? We're doing secant plus tangent. So I get in here, when I add them together, 1 plus x over root 1 minus x squared. That's pretty hideous, huh? Oh well. The x's cancel and you're left with this. It's x over x squared. Blah. I'm guessing it wouldn't have been quite so hard if I took the easy route of starting with a trig sub. So let's see what that would have done. If I did a trig sub here to begin with, this would have been 1 minus sine squared, because I'm saying x is sine theta, dx would be cosine theta, d theta. And then this is 1 over cosine squared with a cosine on top. That's integral of secant. So that's natural log of secant plus tangent. Either way, you have that ugly secant thing to worry about. But anyway, that gets us to exactly, again, I wrote a d theta when I meant to write plus c because I'm going too quickly, but that gets us to exactly the same place, right? You might think they look different, but remember x minus sine theta is x minus x, so they canceled. So either way you get there, this way is faster, but it's still not the prettiest. Cool. Next step, well, next step is, I guess, I check my answers and make sure I'm not doing anything insane. Well, I guess all of this is insane, but who cares? Okay. So we're gonna look at number 1. Cool. All right, everything looks fine. All right, next on the docket are these problems. So let's scoot them down a little so I have room. And okay, I look at this one, I say natural log is great to see because the derivative of natural log is 1 over x. So if I pick this, then everything falls into place immediately. This just becomes the integral of u du, and that's u squared over 2 plus a constant, where u is natural log of x. So u squared over 2 becomes that, and we're done. This one also doesn't look bad. I say to myself, 2x, I don't care about that. I'll just make it a u sub, and then du is 2 dx. I don't have a 2 dx, so I need to balance it out with a factor of 1/2. But then this is just natural log of u du. And hopefully the natural log integral is one you've memorized. If not, you can get it by integration by parts. In any case, the integral is u natural log of u minus u. And again, you can plug 2x in everywhere. Actually, if I plug in 2x for both of these u's, the 1/2 and the 2 will kind of cancel. So I guess it ends up looking sort of nice. So that's x natural log of 2x minus x plus a constant. Okay. And then the final one, I think you're going to need partial fractions for no matter what. So this will be the one where we show how that works. And I think I've done this one in section, but it doesn't matter. Let's go ahead and do it the nice way of picking u to be ln x, picking dv to be x. Then that would mean du is 1 over x dx. V is x squared over 2. And then the rule for this is it's uv minus the integral of v du. Okay, uv gives me these two things, so 1/2 x squared ln x minus the integral of these two things. But those are nice, right? One of the x's cancels, and I'm just left with x over 2. So since it's over 2, I'll pull the 1/2 out. And lo and behold, we get this. 1/2 integral of x will become 1/2 times x squared over 2. So that's 1/4 x squared plus a constant. And now I will check. Okay, everything looks good. While I was looking back, I realized there's actually a third way to solve this integral. So if you want to see that, I mean, you could, I think this is probably the best way to solve it, actually, and it's a shame I didn't think of it. You can factor the denominator, right? That's 1 plus x, 1 minus x. And then if you have a factored denominator, you can do partial fractions. I won't spend a lot of time, but the partial fractions, I think you get 1/2 for each coefficient, for each numerator. And so it should end up looking like this. Is it minus? I think it's plus. So I think that's correct. And then if you integrate this, you get 1/2. Okay, this integrates to log 1 plus x. This integrates to log 1 minus x. And then you're done. And then the question becomes, are these actually the same thing? Are, all of these, well, if I continued that, would you get the same thing? And the answer should be yes. In fact, it is, because I could have written this as x, and then, let's see. Yeah. Well, it's annoying, but they should be the same. Anyway, cool. So we've seen a few ways to handle that. We did that. This is the one that scares me a bit. I haven't thought up a way to do this, but I look at it, I say to myself, can I do u substitution? And then I say no, because derivative of this will still be 2e to the 2x. It won't have e to the x in it. Vice versa, if I pick the denominator as u, it's still not great. And then the one thing that comes to mind, and I don't know if it'll work, but the one thing that comes to mind is this. If there's an easier way to do this. Probably not. The one thing that comes to mind is, how can I get e to the 2x from this denominator? And the answer is, if I square the denominator, and I FOIL this thing out, then e to the x times e to the x is e to the 2x. So again, this will be weird, but I could solve for e to the 2x. So I'd get this. And then I could try plugging this in for the numerator, because then I don't have a 2x in the exponent anymore, and maybe that's nice. Again, there's probably a better way to do this. This is just the way I can think of right now. This is nice because if I split it up into two fractions, the fraction on the left gets some nice cancellation. I'm just left with 1 plus e to the x dx. That I can integrate with no trouble. It's still kind of annoying to do the other two, though. I'd get a 1 over 1 plus e to the x. I guess I'm splitting into three fractions. Minus 2, let's pull the 2 out. E to the x over 1 plus e to the x. Yeah, that looks nice. Well, it looks mean, but there's a nice way to handle it. So let's do this. So integrating 1 gives me x. Integrating e to the x gives me e to the x. I haven't decided how I'm going to do this yet. No, that's actually annoying, isn't it? Okay. It's not a good idea. Oh, it's a very good idea. Okay, I have a good idea. The idea is always something along the lines of, I want my numerator to look like my denominator, but I can't just add e to the x to it, so I have to subtract e to the x. But once I do that, I can split it up into two fractions. So let's write this out carefully, because I'm flying by the seat of my pants here. The first fraction, 1 plus e to the x over itself, is just 1. And then I'd get, I mean, let's just leave that as it is. And then I'd get minus minus, so that's plus, the integral of e to the x over 1 plus e to the x. Minus 2, and you'll notice this integral is the same as that. Haha, so it's ugly, but it's getting nicer. These are effectively the same thing, except one has a 2 in front of it. So, okay, let's rewrite. I mean, this minus 1 minus the integral of 1 dx is just minus x when I work it out, so that's nice. And then here, if I combine these two integrals, because it's sort of like combining like terms, they're the same integrand, so might as well, I just get a single minus e to the x over 1 plus e to the x. The fact that there's so much simplification here tells me there is a smarter way to do this, and I just can't think of it. But anyway, there'll be a constant at the end here as well, but I guess we'll worry about that later. The question now becomes, how do I integrate this? The answer should come to you, actually. So pause the video if you need to think about it, but sorry, I guess these x's will cancel so I can forget about them. So let's just put e to the x here. And then the nice thing to do is do a u sub. If I pick u to be the denominator, du is e to the x dx. So du appears up here, that's why I put a du. 1 over u is 1 over 1 plus e to the x. Oh, so this is actually going to work. I get e to the x minus natural log absolute value of u plus a constant. Plug back in for u. U was 1 plus e to the x. Oh, and that should be our answer. Great. If I check it really quick, it does look correct. So that makes me happy. That's it for everything we covered in section, but there's still the section on improper integrals, which we didn't have time to get to. I just have like 4 of these here, so let's try to knock them off fairly quickly. This first one is definitely an improper integral. It has infinity as one of the bounds. It's probably nice to write it as this. So pull the 2 out. I want to pull the 2 out. Yeah, it doesn't matter. Let's write it as, I guess I like how that is. I like how that is. What I will do is I'll handle the infinity on the top. So whenever you have infinity as a bound, assuming this limit exists, then you're allowed to do this. Usually you don't have to worry about the limit existing, but it'll just work. Okay, so let's forget about the limit for now. By forget about, I mean just keep writing it and don't evaluate it. The integral of 2x to the negative 3 is 2x to the negative 2 over negative 2. So the 2's will cancel and I'll get negative 1 over x squared. Then I have to be careful. I have to plug in 1 and I have to plug in t. But after I do that, I can take the limit. If you want to make sure I did that integral correctly, you could take a derivative here and see if you get back to here. And indeed, you would get 2x to the negative 3. So yeah, that works. So again, ignore the limit until the very end. Plugging in, I would get negative 1 over t squared minus a negative. So that's plus 1 over 1. So plus 1. And looking at that, I mean, we know that as t goes to infinity, this fraction goes to 0. So this works out to just be 1. Great. Okay. I guess you could write next to it, this is convergent because it's a finite number representing the area under the curve. The next one, same story. Let's write it as a limit of an integral that we know how to handle. It's okay, and we know that e to the negative 2x integrates to be negative 1/2. Again, it's sort of the opposite of a derivative times itself. And I have to plug in 0 and t. Then take the limit. So okay, plugging in t gives me, well, yeah, I guess this will be kind of ugly no matter what. E to the negative 2t. And then I get a minus. So it's plus 1/2 times e to the 0, but e to the 0 is 1. So I can just leave it like that. Then you ask what happens when t goes to infinity. Oh yeah, and that's nice because you have a negative on top, or a negative in the exponent. So that should go to 0. I should just be left with 1/2. Cool, so let's write that down. This goes to 0, so you ignore it and just write a 1/2. Also convergent. This one, we got to be extra special careful of because there are 2 places it could go bad. I have infinity as a bound, and I'm possibly dividing by 0. So I need to check when is x plus 4 equal to 0. Well, that happens when x equals negative 4. And notice negative 4 is not in our bounds. Right? Our bounds go from negative 2 and then it gets bigger. So that's okay. We're not going to have to worry about splitting up the integral or anything like that to avoid the vertical asymptote. This means same story. Take the limit. Replace infinity with t. And then we have a formula for this guy. Anything of that form, you just write the natural log for, basically. So natural log absolute value. The absolute value is probably going to be important here. No, I guess it's not, but whatever. X plus 4. And I want to go from negative 2 to t. Okay, so I get natural log of t plus 4 minus natural log, okay, if I plug in -2 plus 4 is 2. So I guess I don't need absolute value bars since 2 is already positive. And I get that. And then you should think to yourself, as t gets big, well, natural log is just going to keep growing, right? There's no horizontal asymptote. It doesn't level out. Natural log blows up. So yeah, this whole thing will blow up. It doesn't matter that you're subtracting a finite number from infinity. You're still going to get infinity. So infinity, which we say is divergent. The integral does not converge. There's actually infinite area under that curve. Final one. I think this one's quick, actually. Again, you should be a little careful, and you should say, make sure this isn't this isn't in our domain that we're integrating. So is x ever equal to 0? Sort of. I mean, we're starting at 0, but you can sort of ignore a simple point. You can imagine you're starting just to the right of 0 and then ask the same question. Well, then take the limit. So yeah, what we're going to have to do to address this fact that the denominator could be 0 is we're going to have to do a limit from that direction. If you don't see why this is what I was trying to say verbally, but it'll be better if I explain it. Here's y equals 1 over x. Let's say, yeah, this is 1. This is 0. So I'm going to want to find the area under this curve. The only thing you're scared about is, like, does this blow up too fast? Like, could it be infinite? And so the way to integrate this guy is to say, okay, I know if I fix some value of t, then I could certainly find this area. That'll be finite, no worries. And then I let t approach 0, right? So it slides to the left. So writing this out, I would say this is the limit as t approaches 0 from the right of the integral. T is replacing my lower bound here, because that's where my vertical asymptote is at 0. Still going to 1. And then same integrand, 1 over x dx. As always, you can kind of do it blindly now until you have to do the limit at the very end. So integrating this thing, 1 over x integrates to natural log of x. Again, I'll put absolute values, but it won't matter in this case. And then I go from t to 1. Again, ignore the limit for now. Just plug in and see what you get. If I plug in 1, natural log of 1 is 0, so that's nice. And then if I plug in t, I don't really need absolute value bars because everything's positive, so I'll just write that. Okay, so this goes to 0. I don't need to worry about that. So I'm really just asking, what happens to natural log as t gets close to 0? And the answer is this. The natural log function looks something like this. As my, I guess this is the t-axis here in this case. So I should have called this natural log of t. As t gets really close to 0, this thing drops to negative infinity. Of course, negative natural log would then go to positive infinity, but either way, it's blowing up. So this would be infinity diverges. Cool. So yeah, that's pretty much all of the problems. So yeah, let me know if you have any questions besides these, and otherwise, yeah, have a good day.